Hey guys, what's going on? So today we are going to be talking about representations of SU2 in 2 dimensions. And this is going to be very important because this is going to be sort of the foundation of everything that's going to come. So without further ado, let's get into the material. But before that, make sure to hit that like and subscribe button if you like this kind of content. Now let's get into the material. So we are talking about representations of SU2 today. So as a teaser, I found this very nice diagram online. This diagram shows exactly what exactly is going to be going down for the next, perhaps, I think, 2 to 3 videos. We're focused on labeling where we get this 1/2 and this 0 from, basically, and where we get this 1 and this 0 from. And these are really just labels, but we're going to find that they can also be regarded as sort of conserved quantities later on in this playlist. This is sort of how this works, right? So we start off at this 0, 0 labeled representation. And then as we increase sort of the number of dimensions in our, the number of dimensions that's sort of representing our group, our Lorentz group, which is what we're going to get to, then each one of these labels represents, or each one of these labels is a label on a specific type of representation of the group that we're talking about. So we can talk about, say, a two-dimensional representation of a Lorentz group, or a 3-dimensional or 4-dimensional or 5-dimensional representation of a Lorentz group, right? And that's how this is going to go. So this axis sort of represents how many dimensions there are that we're going to be focused on. And these, as we go out here on this triangle, we are understanding how each one of these are sort of connected to each other, okay? So what we're going to cover is the left spinner representation and the right spinner representation. But right now we're just focused on labeling. And this is why the videos that we covered in the past were so important. And then we're going to see how these two representations, when we combine them, we get a 4-vector representation as well. And that covers a lot of physics already, right? With spinners, that covers the electrons. 4 vectors, that covers basically everything else that we can sort of fathom in at least our classical sense. And then later on, we'll talk about different higher forms of representation. But for now, we're really going to be focused on the spinner representations and the 4-vector representations. All right. So that's sort of as a teaser. So let's get into how we label these. We're going to get into the 2D representation of the SU2 group. So the way we're going to do this is we take our M max, which is what we talked about in our last video, and we're going to consider all of the possible eigenstates that are associated with that maximum value, right? So if we say our maximum value is 1/2, then all the possible eigenvalues, again, are going to be 1/2 and negative 1/2. Okay? So let's see what happens when we consider J1 acting on this state, right? So this is our first state, and this is our second state. Let's see what happens when we consider one of our generators acting on this guy right here. So we flesh this out like this, right? Because remember, J1 is equal to this right here. Because if you can go back into the videos, you can see how this works out, right? But this is so this is how J1 is defined in terms of what we defined before, and we could split this guy up like this. And what we find out is that, if you recall, J minus is going to act on our second input value in our state, right? So if you go back to our Casimir operators and our Cartan operators, you can go back to that video. You can see exactly how this works. And what you'll find out is that these guys operate on the second input of the state here. So this guy's going to go to 0 because you can't get anything higher than 1/2 in our 2D representation. All right, so this guy goes to 0. This guy goes down to 1/2, and so we get this. Okay? So we can do the same thing acting on the other state, right? So we acted on this guy. Now we're going to act on this guy, which is right here. Get this. This is, again, is a definition that you can sort of derive for yourself, referring back to our last video. I want to keep these videos short, right? So the way I keep these short is either by referring to videos that we've recently seen, or that's the way, right? That's the way we keep them short. I don't want to really bug you down with the boring derivations, the derivations that I at least think are relatively easy to do. Anyways, this again, this is just equal to this because we define J1 to be, we don't define it to be this, right? We define these two guys and then we can get J1 from these guys. But anyways, we get this and then we do the same thing, right? So, but instead this guy goes to 0 because J minus acting on the negative, or the lowest eigenvalue for this J max is going to take us to 0. And this guy is actually going to go up 1/2. So what we have is J1 acting on this state will bring our eigenvalue down, and J1 acting on this state will bring our eigenvalue up. So J1 flips the state vector, right? It flips these two entries. That's what J1 does. Okay. One such matrix that will do this is this guy right here, right? So if we take J1 to equal this, then J1 acting on a state right here is going to flip our vector, right? So J1 is really just flips the state vector. That's what we're seeing right here. Right? So if we take this entry here, we're not really looking at this entry. We're looking at this and this, and we're seeing that J1 is flipping something, right? So the simplest matrix that we can think about, something that flips something else, is something that looks like this. All right. So the 2D, so this is an element of the 2D representation. So if we want to get a group out of this, we can realize, well, this is part of our Pauli matrices. And if we recall, our Pauli matrices can be closed under a group if the other two matrices are these guys. Right? So the 2D representation of our SU2 can indeed be given by our Pauli matrices, which is going to be interesting, again, because then the question becomes, what exactly are the objects that these SU2 matrices act on? Which is an interesting question, right? So we also found, if you recall, that exponentiating our SU2 generators, or our Pauli matrices, gives us standard rotation matrices. And our SU2 generators obey the same commutation relationship as our SO3 generators. So that we're starting to see some connections here, right? The connections we're seeing is that, okay, we have a 2D representation of an SU2 group, and that 2D representation is our Pauli matrices. And if we exponentiate this 2D representation, we get standard rotation matrices. And all of this is sort of connected via the Lie algebra. The Lie algebra, again, which is a commutation relationship, is sort of the glue that holds this entire framework of looking at physics together. We always want to keep in the back of our mind the algebra here, or the commutation relationship between the two. Because again, the commutation relationship between the two defines how these things are sort of closed, right? And if we can find other objects that obey the same algebra, those are also closed. And so the idea here is that all of the elements, you can have a two-dimensional representation that obeys the algebra, but you can also have a three-dimensional representation or a four-dimensional representation that obeys the algebra as well. But if all of those obey that algebra or that commutation relationship, then it sort of begs the question, how are these guys really similar to one another? What exactly are the things that they're acting on? So then that we're going to get to that question, and we're going to see how they're all related to the Lorentz group. So when we talk about these representations, later we want to keep in mind how we label these representations, right? Which is going to be this way right here, right? So this is a little bit different than what we've done here, right? We're labeling states. This is a state. Here we actually want to label representations in this way, where we have two m max values. So we could talk about, say, a 1/2 0 representation, right? So the way we write that is 1/2 0 representation, or a 0 1/2 representation. The reason we do this is because when it comes time to looking at the Lorentz algebra, we're going to find two independent groups that sort of emerge from the Lorentz algebra. And we want to label those two groups and get the representations for one of those two, or for both of them. Okay? And they're independent of each other. They're not. And what we're going to find is that we can label them like this. So here's another picture. If we zoom into this picture, I really like this. This came from the same paper from this guy right here. This is Lorentz group and representations by Isaac Nuttling. I think that's how you say it. I think this is from the same paper. If we zoom in here, we have our 1/2 0 representation and our 0 1/2 representation, exactly what we saw in that other image. And here we have this isomorphism again that we saw in our other image, how these two guys are linked via these straight lines that are not dotted. The dimension of our Lorentz group that we see, that we're interested in, well, these are these blue guys, right? Because if we recall before, the dimension is that constant, the separation constant between our eigenvalues divided by 2, which is what we're seeing here. Okay, and this is what I mean here by the independent matrices, or the independent Lorentz groups that come out of the Lorentz, they don't come out of the Lorentz algebra, say, but they are very closely linked when we begin to consider Lorentz algebra. And what I will say before we close this video is that the Lorentz group, it's important mathematically, right? We will be able to see that the Lorentz group is everything that sort of comes out of the Lorentz group will sort of hint towards SU2 generators. Okay, and then we can find all the representations there. But physically, the Lorentz algebra, the Lorentz group, is associated with preservation of the Minkowski metric. So that's where the physics actually hits the road, or that's where the physics sort of comes in contact here, because the Minkowski metric, that's essential in special relativity. What we're going to find is that matrices that preserve the Minkowski metric under any sort of transformation matrix, essentially, that preserves the Minkowski metric, is going to obey the rules of the Lorentz group. And then we can get the Lorentz algebra from there, and then we can find representations based off of that Lorentz algebra. And what we're going to find out is that SU2 is a representation. The SU2 generators that we see here are representations of a Lorentz group. The question then again becomes, what exactly are these matrices acting on? Because in one case, the four-dimensional case, right, where you have 4 vectors, those guys are going to be those guys are going to be acting on, or the Lorentz group is going to be acting on 4 vectors. But if we have other representations, the question is, what on earth are those acting on? And I've speaking a lot of words here. I'll actually put this into a picture here, because this is actually exciting. We're hinting towards something very mathematically enlightening. So let's see if I can draw a picture here. So our Minkowski metric looks something like this, right? Where we have zeros in the corners here, and what we actually, you know what? I'll write all the zeros out, because what the heck? So this is our Minkowski metric. The idea here is that we want to find matrices. These guys are matrices such that our Minkowski metric is preserved. And what we're going to find is that these are no arbitrary matrices. These matrices, there's only a finite number of these guys. And I actually have an example coming up in our later video as to why these just can't be any matrix. But these guys are going to obey the Lorentz. We're going to say that these guys constitute a Lorentz group. So a Lorentz group is a group that preserves the Minkowski metric. Okay. And then what we're going to find, here's our arrow, and then what we're going to find is that the Lorentz group obeys the Lorentz algebra, or it obeys the relationship that's very similar to something that looks like this. Okay, well, this is the realization, right? This right here is our realization. This is our realization, which is super important. The realization is that, well, we already know objects that obey this algebra. That is going to be stuff like the Pauli matrices. But these guys are not 4 dimensions, right? So you need 4-dimensional matrices to preserve this guy. But these guys are not 4 dimensions. These are 2 dimensions. So the question here becomes, okay, well, these guys here, they operate on 4 vectors. What about these guys? Pauli matrices, what on earth do they operate on? Well, generally speaking, operate on, we'll say, 2 vectors. So this idea here, there's a discrepancy, right? These guys, if they're essentially the same because they obey this algebra as these guys, well, they can't operate on 4 vectors because they're only 2 by 2 matrices. So what the heck? like what the heck is going on here? Well, the idea is that these guys are going to flip. These guys are going to flip entries on 2 vectors, and the flipping of those entries corresponds to flipping between right and left chiral spinors. And these guys, again, they're operating on our classical 4 vectors, or 4 vectors that are associated in special relativity. Okay. And so there is an equivalence between this here and this right here, and we're going to find out what that equivalence is. And then there's going to be the question of, okay, well, these guys are matrices, these guys are matrices. There's actually going to be a continuous version of these as well, right? So matrices are discrete, right? You move by some angle, say. But what we'll actually also find is that these guys, this Lorentz algebra can also be attained through something that we'll call something that looks like this. Right, this is our continuous thing that these will act, something like this, an object that looks like this will actually also obey this relationship, and we'll see why, right? We'll see why, but that's going to be a later video. And so what we're going to do, this is actually going to be quite interesting. What we're going to do is we're going to find all of these. We're going to find all these guys. So we found these guys. We're going to work on these guys next. Then we're going to work on these guys. We're going to bunch that all together into a single equation, and we're going to call this the Lorentz algebra. Okay, and then we're going to move on from there. And moving on from there, we're going to be talking about isospin. We're going to be talking about quarks. We're going to be talking about a lot of interesting stuff. We're going to be talking about how then we can get from these guys to Lagrangians, because ultimately we're interested in Lagrangians, right? Lagrangians, that puts us in the world of classical field theory and then quantum field theory, right? So there's going to be a lot to come. Again, if you want to see this kind of content ahead of time, you can go onto my Patreon page. If you're completely okay waiting a couple of days, I have these videos coming out every Wednesday and Saturday. Then hang out every Wednesday and Saturday and watch these videos, and I hope to see you guys in the next one.